In the last class, I have introduced the concept of invariance in a estimation problem. So what do you mean by invariance? Invariance means that there is some sort of symmetry in an estimation problem, and therefore we introduce a group of transformations under which we can apply it on the sample space. If we apply it on the sample space, there is a corresponding transformation on the parameter space, and therefore there is a corresponding transformation on the space of estimators. So we choose a loss function which remains invariant, and then we derive the form of an invariant estimator. And if the estimator is invariant, within that class we try to find out the best choice. In the previous class, I gave you one example, that is of the estimation of the mean of a normal distribution when the variance was taken to be unity. And we showed that the usual sample mean is actually the best location invariant estimator. Okay, I'll proceed with some theory here. So first of all, what is an invariant function? So we say that a function phi is invariant with respect to a group of transformations G, if we have that phi of Gx is equal to phi of x for all x and all G belonging to G. And then we look at what is maximal invariant. Like you had the sufficiency and minimal sufficiency. Similarly, in the invariance, you have the concept of maximal invariant. So a function, say Tx, is said to be maximal invariant under a group G if it satisfies two conditions. First condition is that it should be invariant, and the second condition is that if two points are taking the same value under the function t, then they must be linear transformations of each other. This means x2 is a transformation of x1. Of course, it means that x1 is a function transformation of x2 because you can take G inverse here. Okay, so it means that an maximal invariant is actually constant on the orbits. T is maximal invariant if it is T takes constant value on orbits, and second, it takes different values on different orbits. So like minimal sufficiency, this is something like a maximal concept actually. So there are invariant function. What is maximal in that particular group, okay, with respect to that group and with respect to a given space of values, that which we call sample space. I hope this statement of the definition is clear, the maximal invariant. We will prove some small property of this. Let us call it a lemma here. Let Tx be maximal invariant with respect to G. Then a necessary and sufficient condition for phi to be that phi depends on x only through Tx. That is, phi x is equal to some beta of Tx. I am not writing down the proof of this. It is slightly complicated because it involves a little bit of measure theory. So I will not write that here. So let us look at some examples of this maximal invariant here. Suppose I take the sample space to be n-dimensional Euclidean space, and let us consider the group of transformations so it is n-dimensional. So G of x, so at the point C, we are defining as that each of the values is translated by same number, okay, where C belongs to R, okay. Now for invariance, what do we need? For invariant function T, you will need T of x1 plus C and so on, xn plus C equal to T of x1, x2, xn, because it should not change. T of GCX is equal to T of x for all x, okay, and for all C. So we can choose, say C is equal to minus x1, for example. Then what you will get? On the left side, you will get T of 0, x2 minus x1 and so on, xn minus x1, that is equal to T of x. So on the right hand side, you are getting this as a function of x2 minus x1 and so on, xn minus x1. So we conclude that x2 minus x1, x3 minus x1 and so on, xn minus x1, this is maximal invariant, because this is invariant under this transformation. And if I take 2 points equal in this under this one, then it will satisfy that one of them is the transformation of the other under the constant value. See, let me show you here. See, if I take 2 points x and y at which the value is equal, then what does it imply? It implies x2 minus x1 is equal to, say, y2 minus y1. So I can write it as something like x2 is equal to y2 plus x1 minus y1. If I am writing, say, x3 minus x1 is equal to y3 minus y1, then I can write it as x3 is equal to y3 plus x1 minus y1. So everywhere you will get this. So this can be considered as C. Okay. So x is GC of y, where C is x1 minus y1. I hope this example is clear. Let me give with respect to scale group also. Let us see how the invariant function is constructed. So again, let us consider, say, X to be the n-dimensional Euclidean space, and I consider the group to be the group of scale multiples here. GCX is given by CX1, CX2, CXN, where C is, say, a positive number. Okay, and here I may consider, say, this to be Rn plus. Okay, that means on the positive quadrant I am taking. I am taking this positive because since here multiples are there, so if I consider 0 or divisor is coming, then it will create problem. So therefore I am taking Rn plus here. Okay. Now let us put this condition, T of GCX is equal to T of X. Okay. Then this will imply T of CX1, CX2, CXN, that is equal to T of X for all X and for all C positive. So let us choose here, say C is equal to 1 by X1. Then this will give me C T of 1, X2 by X1 and so on, Xn by X1, that is T of X. That means this is a function of x2 by x1 and so on, xn by x1. So maximal invariant is that is x2 by x1, x3 by x1 and so on, xn by x1. We can show here, suppose I consider Sx is equal to Sy. Okay. Then I am writing x2 by x1 is equal to y2 by y1, which will imply that I can write x2 as, say, y2 into x1 by y1. So this I can take as C, because if I take, say, x3 by x1 is equal to y3 by y1, then this implies x3 is equal to y3 into x1 by y1. So this is acting as C. So this is maximal invariant. Okay, are these examples clear to you?
Sir, once can you go to necessary and sufficient condition of 3 slides?
This one? So
Yes.
T is maximal invariant with respect to G. Then a necessary and sufficient condition for phi to be invariant is that phi depends on X only through, sorry, this is maximal invariant. Phi depends on X only through Tx. So that is the thing.
Yes, sir, understood.
I am not writing the proof here. Actually, one part can be immediately written, that sufficiency part, but for necessity part, there is little bit of argument required. So I am not writing the proof here. But I think from the examples, it must be very clear. the two examples that I have given. If I consider, say, n-dimensional Euclidean space, and G is the group of all the permutations, okay, X is giving a permutation xi1, xi2, xin, okay. So these are all permutations for all i1, i2, in belonging to 1 to n, okay, all permutations. The group of all permutations. If we consider that, then the maximal invariant is the set of ordered statistics, because this will remain invariant under all permutations, okay. Let me move to implications of invariance in the estimation problems, starting from the effect on sufficiency, etc. See, we have seen that Raoub equalization holds. That means given any estimator of a parametric function, I can take conditional expectation of that parametric function with respect to the sufficient statistics. In general, that estimator will have a smaller mean squared error than the original estimator. So sufficiency concept should always be utilized. Now the question comes that if I have sufficiency as well as invariance, then which one we should use first? Then the general guideline is that firstly implement sufficiency, because firstly if you use invariance, and if the invariant function is not a function of sufficient statistics, then again you can improve upon that. So it is better that if we restrict attention to the functions based on sufficient statistics and find the maximal invariant there. So the example of the normal distribution which I did it in the last class, there I have taken x bar only, because x bar was a sufficient statistics there. And of course, there it turns out that the x bar was the best translation invariant estimator of mu. Okay, so let me just put that as a comment here. I mean, of course, you may question this thing that if I firstly do invariance and then sufficiency, then what is the difference? Whether the results will be somewhat different. The answer is that the set of actually in decision theory we do what are the desirable estimators in the estimation theory, because I have told that there is nothing called the best in general. So basically you have some things which are good. So if you consider the class of good estimators, then whichever property you apply first, like sufficiency and then invariance, or invariance and then sufficiency, it turns out that the set of good procedures is equivalent. Okay, so there are certain research papers on this actually, but I would not get into those things in this particular course, because at your level we will not be able to do that. Actually, there are papers on sufficiency and invariance. There are large number of research papers starting from 1980s actually, but I will skip that part. So in general, right now what we are accepting is that firstly we apply sufficiency and then invariance. So let me just take up some examples here. Some of the examples that you already done. Okay, we'll take up that now. So do you remember this exercise? Let x1, x2, xn follow uniform 0 theta, okay, where theta is of course positive, and consider estimation of theta. So you all remember this problem?
Yes, sir.
What are the things that we already obtained there? We obtained the method of moments estimator, okay. T1 that is equal to 2x bar, that is the method of moments estimator, isn't it? Then we had T2 which we call xn, that is the maximum likelihood estimator. Then we had T3 that is n plus 1 by n xn, that is the uniformly minimum variance unbiased estimator, because here xn is complete and sufficient statistics. You remember this because we have discussed this problem in detail, okay. So this thing you remember very well.
Yes, sir.
Yes, sir.
Now see, here comes something interesting. Now I have introduced another concept. See, we had initially the method of moments and then the maximum likelihood estimation, and actually we showed here that method of maximum likelihood estimator gives you an estimator which has a smaller mean squared error than the method of moments estimator. And of course we derived UMB also, and actually we have compared the mean squared errors of all the three estimators, okay. So which one was the best? Do you remember here in this particular problem? Among T1, T2, T3, certainly T2 was better than T1. But between T2 and T3, which one was better with respect to the mean squared error?
T3.
T3 was the best. Okay, so one has a general understanding in this particular problem, if you don't know anything else, that if a problem is given where some small sample size is there, we would like to use n plus 1 by n xn as an estimator for theta, okay. That is the general understanding. Suppose I have a sample of size n is equal to 6. Suppose this is some medical problem, or it's a clinical trial, or it's a say industrial problem with some heavy duty experiment. So n is equal to say 5 or 6. Suppose I say n is equal to 5. So you will prefer to use 1.2, the maximum of that thing, that is x5, and compare to say x5 or compare to 2 times the mean of the observations, okay. Now let us look at whether invariance does something different here, okay. Consider the loss function. So we are estimating theta. So mean squared error is basically theta minus a square, okay. But what we do, we will divide it by theta square. That means you can actually consider it as 1 minus a by theta square. Basically, what does it do? It actually scales up, because here we want to make it free from the units of measurement. Now let us look at it. Consider a scale group of transformations. Okay, so G is equal to GC. Now another thing that you note here, sufficient statistics is Xn. Okay, so we need not bother about original X bar or X1, X2, Xn, etc. We can restrict attention to estimators based on Xn alone. And therefore, if I consider this group, that is GCX is equal to Cx, I will implement it on the set of values of Xn, okay. So Xn of course belongs to some X, so it is implemented on that. And what is the distribution of Xn? Anybody knows that? We have used it earlier. What is the distribution of that is ny to the power n minus 1 divided by theta to the power n. Okay. Let us look at the effect of this. What is the distribution of, say, c times xn? Suppose I call it u. Okay, c times xn. So what is the distribution of that? If you consider simply this kind of transformation, so in the density, if you put it, the density of u will become n. So this is u by c to the power n minus 1 by theta to the power n, 1 by c, and 0 less than u less than or equal to c theta. Okay. So we can write it here properly. The density of u as n u to the power n minus 1 divided by c theta to the power n, 0 less than u less than or equal to c theta. So you look at the comparison between these two distributions. Here theta is now replaced by c theta. Okay. That means if I am considering the distribution of c times xn, theta goes to c theta. So this family of distributions is invariant under this group of transformations. So the family of distributions, earlier I have given you the example that uniform 0 theta is invariant under the scale group, but even the distribution of the maximum of the observations is also invariant. So family of distributions of xn is invariant under the group G, and the G bar group, that is on the parameter space, also it is same thing, that is GC theta is C theta. Okay. Now let us check that with respect to the loss function that we have considered here, that is this particular loss function. If this is invariant, then what is the form of invariant or equivariant estimator, and based on that, how to find the maximal invariant. Okay. So let us consider this condition GC bar theta GC tilde A, that should be equal to L theta A, isn't it? We want this condition. So this will give, so GC bar theta is C theta. So if you substitute here 1 minus A by theta, so what you will get? 1 minus GC tilde A by C theta square. This should be equal to 1 minus A by theta square. So this implies that GC tilde A should be equal to C of A. So this is the induced group of transformations on the estimation space, and then the estimation problem becomes invariant estimation problem. So the problem of estimating theta is invariant under group G when the loss function, so this loss function actually we call to be scale invariant loss function. Okay. Okay, so is this okay to all of you? Did you understand this, what we have done? Are these steps
Yes, sir.
clear? Now we want to find out, yes.
So can you explain that, like we have written LGC theta, comma J tilde theta equals to L theta comma A.
So this is the condition for the invariance of the estimation problem, that is the loss function should be invariant. So under the transformation GC, theta goes to GC bar theta and A will go to some GC tilde A. And this value should not change. It should remain invariant under all the for all this thing and for all C. Okay. So I need this thing 1 minus GC tilde A by GC bar theta. Now, of course, GC bar theta we derived just now, it is C theta. So this square should be equal to 1 minus A by theta square for all this thing. So how this will be possible? Only if you have GC tilde A is equal to CA. Then only this condition will be satisfied, because we want it for every value. That means for all theta, for all A, and for all C. So if this is taken, then the problem is invariant. Okay. Is it clear? This point is clear to you?
Yes, sir. Thank you, sir.
Now, the form of an equivariant estimator, say delta xn, because we are basing it on xn, okay, under group G. Let me put here capital Xn, okay, because small we use the value and capital we use the notation for the variable. So what we want, delta of G C Xn equal to GC tilde delta of Xn. Okay, we will like to have this for all C and for all Xn. So this means delta of Cxn is equal to C times delta of Xn for all C for all Xn. So what we do, we choose here C is equal to 1 by Xn. If we do that, then this left hand side becomes a constant, and this is 1 by Xn delta of Xn. This means delta of Xn I will choose to be, this is some constant, so some k times Xn. So I'll put it here k. This is the form of an equivariant estimator. That means all the multiples of Xn, they are equivariant estimators under this group of transformations, under this scale group. Okay. If I am considering estimators based on Xn, then all scale multiples of Xn, they are the scale equivariant estimators here. Is this point clear? So you look at this, I wrote this basic estimators here. That is the maximum likelihood estimator and this uniformly minimum variance unbiased estimator. They both are multiples of Xn. T2 has multiple 1 and T3 has multiple n plus 1 by n. So now it is of interest to know or to find out whether, like you said, that T3 is better than T2. So whether we should stop at T3 or there can be any other choice also. So since we know certain mathematics regarding the maxima minima kind of thing, so let us consider the risk function of the estimator. Good afternoon. So now let us consider the risk function of estimator delta k. So that is expectation of 1 minus k times xn by theta square. Okay. So we have to minimize this with respect to k. Of course, we can write the expression and then minimize, or we can minimize first and then write the expression. Both the ways it is all right. Okay. So let us just write it here. This is equal to 1 plus k square by theta square expectation of xn square minus 2k by theta expectation of xn. Okay. So minimizing, see here you can see that k square has a positive coefficient. So therefore, if you do two derivatives, you will get a positive value. That means it's a convex function. So minimization occurs at first derivative equal to 0. Okay. Minimization of r with respect to k occurs by equating first derivative to 0. So 2k by theta square expectation of xn square minus 2 by theta expectation of xn is equal to 0. This means k is equal to theta times expectation of xn divided by expectation of xn square. Is that okay? The minimizing choice, that is theta into expectation of xn divided by expectation of xn square. Is that okay?
Yes, sir.
And can you tell me immediately, because I wrote the distribution of xn, so can you tell me immediately what is expectation of xn and what is expectation of xn square? Okay, maybe you should tell just 1 minute to tell me the answer.
N theta by n plus 1 and n theta square by n plus 2.
Okay, so you are telling something n by n plus 1 theta. Okay, now the second one.
N theta square by n plus 2.
N by n plus 2 theta square. Okay. So you can simplify, this is equal to n plus 2 by n plus 1. Now this is something surprising. The best choice is neither the MLE nor the UMVUE. In fact, you have now come up with the, so the estimator let us call it delta or T4, I can call it, okay, some other name I will give. T4, that is n plus 2 by n plus 1 xn is the best scale equivariant estimator of theta based on xn. So we will prefer T4 over T1, T2, T3. So this is actually what I wanted to convey from the beginning, that this concept sometimes leads to different and better estimators. So when we did the concept of maximum likelihood estimation and when we did the concept of uniformly minimum variance unbiased estimator, we stopped at T2 and T3. But now we have got something different. Okay, and this in the class of scale equivalent estimators based on theta, based on xn, actually this is the best estimator. So we would certainly prefer, because this is based on a loss function. So basically it covers the mean squared error here. Is that okay?
Yes, sir.
Okay. Let me take up another interesting problem here. So let us take, say, x1, x2, xn following normal 0 sigma square. Okay, normal 0 sigma square usually we consider when mu is known. When mu is known, then we can shift by all the observations by that value so that we can make the mean to be 0. So this is one of the estimation problems which usually occurs in statistical inference. So that is why we are considering all this kind of problems. Sigma square, of course, is positive. I am just putting this sigma also to be positive because it is on the positive side of this one. Okay. Now this problem also we have discussed earlier. If I consider, say, sigma xi square, this is complete and sufficient statistics here. And if we consider, say, t is equal to 1 by n sigma xi square. So if I use some notation, say w is equal to sigma xi square, okay, then this is 1 by n w. This is the MLE and it is also UMVUE. Do you remember this? When we are discussing different concepts, each of these models I have considered in detail. Do you remember this, that it was maximum likelihood estimator as well as the UMVUE? This follows actually from the fact that W by sigma square, suppose I call it U, then that is having a chi-square distribution on n degrees of freedom. So expectation of U is equal to n. So that gives you the unbiasedness, etc. And MLE, of course, you can derive directly. Now let us consider here this concept of invariance. Okay. Okay, so first of all, since complete sufficient statistics is W, we will consider based on that only. There is no need to consider estimators based on all xi's, because once we have the complete and sufficient statistics, we can restrict attention to that. So we will consider based on, so this I put as, say, C square W. Okay. We can put CW also, but here, because if you consider, say, basic xi is going to CXI, then what will happen to xi squares? They will go to C square xi square. So I will consider the transformation in that sense only. Otherwise, there is no problem if you consider CW also. The outcome will be same. Okay. Now under this group, and let us consider, say, loss function in estimating sigma square as, again, the scale invariant loss function I will consider. Okay, so look at the distribution properties and so on. What is the distribution of W? Okay, I think some of these things you are knowing, but maybe you will forget again. So let me maybe write it here. See, the distribution of xi's is normal 0 sigma square. So you can write the distribution of xi by sigmas, that is normal 0, 1. So the sum of the squares becomes chi-square on n degrees of freedom. That is the statement that I have written here. Okay. So from here you just try to work it out. Let us write it in the backward fashion so that you can understand the process of writing down the densities and so on. So this is 2 to the power n by 2 gamma n by 2 e to the power minus u by 2 u to the power n by 2 minus 1. Okay, that is the distribution of u. Now W is sigma square u. Okay, so we can write the density of W is sigma square u. So if I consider the transformation here, du is 1 by sigma square dw. Okay, so the PDF of W is, we have to write for W because we are considering the scale invariance. So on W we have to consider, otherwise the full property you cannot understand here. So 2 to the power n by 2 gamma n by 2 e to the power minus, so u is w by 2 sigma square, and then w by sigma square to the power n by 2 minus 1, 1 by sigma square. W is positive. So we can put it in a simplified fashion like this, 1 by 2 sigma square to the power n by 2 gamma n by 2 e to the power minus w by 2 sigma square w to the power n by 2 minus 1. So this is the probability density function of sigma xi square. Now if I am implementing this group here, c square w, then what happens to this? Actually I can put c itself, I think, just to avoid confusion, because sometimes it may lead to little bit of, yeah. So now I define V is equal to CW. What is the distribution of this? That means W is equal to C V by C. So dW is equal to 1 by C dV. So what is the distribution of V? That is 1 by 2 sigma square to the power n by 2 gamma n by 2 e to the power minus W by, so W becomes V by C. So V by 2 C sigma square W, this W becomes V by C to the power n by 2 minus 1, 1 by C, where V is positive. So this becomes equal to 1 by 2 C sigma square to the power n by 2 gamma n by 2 e to the power minus V by 2 C sigma square V to the power n by 2 minus 1. This is the probability density function of CW. So from the density function of W, if you compare, so this is the density function of W, 1 by 2 sigma square to the power n by 2 gamma n by 2 e to the power minus W by 2 sigma square W to the power n by 2 minus 1. Okay. So now by transformation it has become 1 by 2 C sigma square to the power n by 2 gamma n by 2 e to the power minus V by 2 C sigma square V to the power n by 2 minus 1. So you can see here that sigma square has been changed to C sigma square. So the family of distributions of W is invariant under this group of transformations. So under the scale group G, this is invariant. Now let us look at the effect on the loss function and then what is the form of equivariant estimator here. So we should have L C sigma square GC tilde A is equal to L sigma square A for all C, for all A and for all sigma square. Now this is 1 minus GC tilde A by C sigma square whole square, that is equal to 1 minus A by sigma square whole square. This implies that we should have GC tilde A is equal to CA. Okay. So the estimation problem becomes invariant. So the form of an equivariant estimator based on W. So delta of GC W is equal to GC tilde delta of W for all C for all W. Okay. This means delta of CW is equal to C times delta of W. So choose here C is equal to 1 by W. So we will get delta 1 is equal to so if I put C is equal to 1 by W, I get delta 1 is equal to 1 by W delta of W. So the form of an equivariant estimator is that is delta KW, it is equal to, because this delta 1 I can write as a constant, so KW type. So it's a multiple of sigma xi square. So of course your UMVUE or the MLE, that is also a multiple here. So of course then the natural question arises whether this can be improved. So we can find the best choice. Okay. So consider the risk function of delta K. So risk function, that is expectation of 1 minus KW by sigma square whole square. Okay. So that is equal to 1 plus K square expectation of W square by sigma to the power 4 minus 2K by sigma square expectation of W. Actually, we can write all these values because W by sigma square is W by sigma square is a chi square n. So we already know the moments of that. So in terms of that, we can easily write down this so that the calculations becomes quite simple. So this is K square expectation of U square minus 2K times expectation of u. So the minimization, again you can look at that the multiple of k square is positive, therefore it's a convex function, and therefore the minimization will occur at the derivative equal to 0. So this gives you k equal to expectation of u divided by expectation of u square, because you will get 2k expectation u square minus twice expectation u is equal to 0. So k becomes expectation u by expectation u square. So here you look at the values of this one. Expectation of u will be n, because this is chi square n distribution. So in chi square n, you know that the first moment is n and the second moment is n square plus 2n. You remember that? So this gives us the best multiple as n plus 2. So let us put it as say t star, that is equal to 1 by n plus 2w is the best scale equivariant estimator of sigma square based on xn, not xn, based on w. So here again you see that there is a surprisingly new thing coming here. Like we got MLE and we proved that it is also uniformly minimum variance unbiased estimator in this problem. But what we are getting here is that they are not the best. In fact, within the class of scale multiples of W, we get a choice which gives a smaller mean squared error here. So this will be preferred, even, I mean, especially for the small sample sizes. For large sample size, of course, they may become almost equivalent, but for small sample sizes, certainly it will make a difference in the value of the risk function. Okay, so is this problem clear to you?
Yes, sir.
So let us take up another exercise here. So I consider a random sample from a general normal distribution, that is mu sigma square, where mu is any real and sigma is positive. Okay. And let me consider two different problems here. Okay. Let me consider one loss function L1. That is mu minus d by sigma square. You can consider this as the problem of estimating mu. And another one I consider problem of estimation of say sigma square. So something like 1 minus d by sigma square whole square. That means the function which I wrote earlier just in the previous case. Okay. So I am considering these two estimation problems if I have both the parameters mu and sigma square unknown. Let us look at certain group of transformations here. See, this problem we have handled extensively. We found the method of moments estimators, we found the maximum likelihood estimators, we found the UMVUs for this one. So for x bar, for mu, x bar is MLE, it is also UMVUE. Okay, that we have already proved. and for sigma square 1 by n sigma xi minus x bar square, this is MLE, and 1 by n minus 1 sigma xi minus x bar square, that is UMVUE. So these things we have already answered. But now let us see if by employing this invariance some new thing will come or the old thing will remain. Okay. So since it is a 2-parameter situation, I will consider another group. If you remember, this normal distribution is actually having the linearity property. That means under any linear transformation, the distribution of random variable remains normal with modified mean and variance. So that gives us the idea that we should use the group of linear transformations here. So we consider the group which we actually call affine. In statistical terminology, they have another name here. So you should be familiar with that. That is G, let me call it GA. Okay, so GA group is G of, say, something like BC, where G of BCX is equal to BX plus C, where A is B is positive and C is any real number. We will actually consider it on the complete sufficient statistics. For this problem, do you remember that x bar s square is complete sufficient? Okay. So what will happen if I employ this thing here? X bar will go to, so x bar s square, that will go to b x bar plus c, and this will go to b square s square. So that means if I consider the distribution mu sigma square, that will go to b mu plus c and b square sigma square. I think these are all very clear cut things. There is not much difficulty to understand this. Is that okay?
Yes, sir.
Now the interesting part comes that we want to determine for these two problems, estimation problem of mu and estimation problem of sigma square. For this, the form of the equivalent estimated, etc. That is interesting. So let us look at that. So for L1 loss function, that is estimation of mu, so what do we have? L1 of, so we have b mu plus c, b square sigma square, and here what will be the effect? That is g of bc tilde d, that is equal to L mu sigma square d. And of course, we have to again and again write the same thing for all b greater than 0, c belonging to R, and all those things. So what this gives us? So L1 function is mu minus d by sigma square. So this gives you b mu plus c g tilde bc d square by b square sigma square. So this is mu minus d square by b square, sorry, sigma square. So we should have G tilde BCD is equal to BD plus C, because then C will cancel out and then B square will cancel out in the numerator and denominator. So the estimation problem of mu is invariant under this group of transformations. So the form of an equivalent estimator, if we want to find out, then we should have delta of GBC, and this is applicable on x bar s square. Okay, that is equal to G tilde BC delta of x bar s square for all B, C, x bar, s square, etc. So that is delta of B x bar plus C B square s square, that is equal to B delta x bar s square plus C. So what we can do, we can choose here, say C is equal to minus B x bar, and then I can choose B to be, say, 1 by S. If we do that, then what I will get, this will become delta of 0, 1, that is equal to 1 by S delta x bar s square plus minus bx bar. So this is some constant. So the form of an affine equivariant estimator of mu is delta k times x bar s square is equal to, so this b we have put as 1 by s. So let me write it here. So this gives you x bar plus some constant times s. So this is the form of an affine equivariant estimator of mu. Okay. So it is dependent upon a single constant here. Therefore, the minimization problem makes sense. That means we can consider we now try to find the choice of k such that the risk of delta k is minimized. So R mu sigma square delta k, that is expectation of x bar plus ks minus mu by sigma whole square. So we can actually split it, because in normal distribution we have some nice properties. We can write it as x bar minus mu by sigma whole square plus k square expectation of s square by sigma square minus 2k expectation of x bar minus mu by sigma into S. Okay. This is, of course, I can keep it outside also, there is no problem. This is sigma square here. So you can substitute all these terms here because we already know this is variance of x bar, that is sigma square by n divided by sigma square. So this becomes 1 by n plus k square, and expectation of s square is sigma square, so this becomes 1. And here x bar and s are independent, so you can write it as a product of expectation of x bar minus mu into expectation of s. So this is 0, so this goes away. So you are left with only this part. So minimization occurs at k equal to 0. This is minimized at k equal to 0. So delta 0, that is equal to x bar plus ks. So k is 0 means it is x. So this is also the best affine equivariant estimator. So in the estimation of the mean of a normal distribution, in some sense x bar remains very good estimator because it is satisfying so many properties. Best affine equivariant estimator of mu. Okay, so this is some nice property that we are able to get. Okay, is this calculation clear?
Yes, sir.
Yes, sir.
Now let us look at the estimation problem of sigma square, that is under the loss function L2. For estimation of sigma square under the loss L2, now we require L2, of course all these things are there, that is b mu plus c, b square sigma square, and gbc d, that is equal to L2 mu sigma square d. That means, so here what was the function? It was 1 minus g tilde bc d divided by b square sigma square whole square, that is 1 minus d by sigma square whole square. So this will be true if gbc d is equal to b square d. So the estimate of sigma square must get multiplied by b square. Is that okay? So the form of an affine equivariant estimator of sigma square, we should have delta of okay, so let us write it in the complete sense. That is, we should have a x bar b x bar plus c b square s square, that is equal to b square delta x bar s square. We want it to be true for all b x bar s square etc. So here you choose c is equal to minus bx bar and b is equal to 1 minus 1 by s. So this will give me delta 0, 1 is equal to 1 by s square delta x bar s square. So the form becomes, this is some constant. So that is delta x bar s square is a function of a multiple of s square only. So this is the affine equivalent estimator of . So it is surprising here, you started with full x bar s square, but an affine equivalent estimator of sigma square is simply a multiple of s square. So here you look at this, we have the available estimators 1 by n sigma xi minus x bar square, 1 by n minus 1 sigma xi minus x bar square. So both of them are multiple of s squares. This is of course I am calling to be s square, okay, and this is nothing but n minus 1 s square by n. So these are our two estimators which we know already. Let us just put it here. And that is T1, that is equal to s square, that is UMVUE, and T, let me call it T2. T2 is n minus 1 s square by s square, that is the MLE. So both of these are in this form only. Now let us see whether something else is possible, or like mean of the normal, there is no improvement. That means we get the same estimator as the best. So let us just try this out. So risk function of delta k, that is expectation of 1 minus delta k by sigma square whole square. So this is equal to expectation of 1 minus k s square by sigma square whole square. These things we can write because we can put say s square by sigma square as say some w. Okay. So what is expectation of w? That is 1. And what is expectation of w square? Can anybody tell me these things? Because we already know the distribution of n minus 1 s square by sigma square. Anyway, I think let us write it fully. I think let me not skip the term. Let us put it properly. Yeah, let me put it properly. The full term. Let me write here. Okay. So this is equal to 1 minus 1 plus k square expectation of s to the power 4 by sigma to the power 4, and minus 2k expectation of s square by sigma square. So if I consider the minimization problem, again because of the convexity, we just have to look at the derivative equal to 0. That's all. That will give us the solution. So 2k expectation of s to the power 4 by sigma to the power 4 minus twice expectation s square by sigma square is equal to 0. So this gives us simply k equal to expectation of s square by sigma square divided by expectation of s to the power 4 by sigma to the power 4. So here we do a little bit of manipulation. Actually, if I define w is equal to n minus 1 s square by sigma square, then that is chi square on n minus 1 degrees of freedom. So the moments of that is well known. Expectation of w is n minus 1, and variance is twice n minus 1. So expectation of w square becomes n minus 1 square plus n minus 1. So that is n square. If I write it as n minus 1 square plus n minus 1, that is giving me n square into
2 into n minus 1 plus n minus 1.
Yeah, n square minus 1, that will give me. Okay, that is n minus 1 into n plus 1. So let us adjust all these coefficients here. So this is n expectation of S square by sigma square, that is 1. So let me just put it as 1. And this one will become n square minus 1, or here you will get n minus n minus 1 by n plus 1. Just check it, check the steps here. Is it okay? N minus 1 square by, yes, I think that's what we will get here. You just adjust these terms here. N minus 1 will adjust on both the sides. So I will get n minus 1 square in the numerator, and in the denominator it will become n square minus 1. That is n minus 1 by n plus 1. So let me call it T3, that is n minus 1 s square by n plus 1. Or we can write it like this: 1 by n plus 1 sigma xi minus x bar whole square. This is the best affine So again, we have come up with a effective implementation of the concept of invariance, because we already knew the UMBUE and the MLE. Among them, we knew the comparison also, that the MLE has a smaller mean squared error than the UMBUE. But now we have, in the terms of mean squared error, something better. The mean squared error of 1 by n plus 1 sigma xi minus x bar square is better than the mean squared error of both the MLE and the UMBUE. Okay, so this definitely leads to certain surprising results. And actually, when we are considering the estimation problem, our desirable thing is to have the lowest risk function. So of course, we said that overall minimization is not possible, but certainly within a certain restricted class of estimators, we can find the best choice. And many times it is leading to certain nice things. So we have seen in the uniform distribution, for estimation of the scale parameter, we got some better choice, that is n plus 2 by n plus 1 xn. And in the case of normal distribution also, now we are seeing that for the estimation of sigma square, we are getting a better choice as far as the mean squared error is considered as a criteria of estimation. So I hope it is well understood. Is the calculation and this procedure clear to you?
Yes, sir.
So I give one exercise here. I have introduced earlier the quantile problem, that is mu minus sigma, mu plus sigma, mu plus minus 2 sigma, mu plus minus 3 sigma, in general mu plus eta sigma kind of thing. So consider the problem of estimating. So let me give it a new name. Theta is equal to mu plus eta sigma, where eta is actually phi inverse p. then this is actually the pth quantile of this distribution. That means probability of x1 given theta, that is equal to p. This is the pth quantile. So I am interested in estimation of this. Okay. Find method of moments estimator of method of maximum likelihood estimator, UMVUE, and best affine equivariant estimator of theta. Okay, so this is the exercise that I am leaving for you. You should work it out. Since now you already know the method of calculation, so it should not be very difficult. Only thing is that it is slightly lengthy. You have to write a lot of calculations. So I mentioned to you that we can consider restriction of the class of estimators. So either through certain criteria like unbiasedness or through invariance, and then try to find out the best choice among them. That is one way of looking at this problem of having estimators with smaller mean squared error or smaller risk function. In general, we have seen that the risk functions are functions. So that means over the parameter space, they may take different values. Some may have higher value, some may have lower value, and so on at different places. So these are the things. If somehow I can reduce this function to a single value, which we say as a representative value. So if each function can be reduced to a single representative value, then they can be compared because the real line is ordered, isn't it? So set of real numbers is ordered. So another way of finding out optimal estimators is by introducing additional criteria. Okay, so I will give you two criteria. One is the so-called Bayes principle, and second is the minimax principle. Let me explain these principles. What do they mean, and then how they are implemented. So let us firstly consider the Bayes principle. So if you look at this functions which I have made here, see on this side you have theta, on this side you are plotting r theta delta. So this is, say for example, r theta delta 1, this is the risk function of delta 2, this is the risk function of delta 3, and so on. These are the risk functions. If over this space I can take some sort of average here, because theta takes values over a space. I mean, theta takes values over the parameter space. So many values are there. If I can define some sort of weighted values of that, so something like a weighted probability distribution for theta, then I can take the expected value of this r theta delta 1 with respect to that distribution of theta. So naturally, if I can take for delta 1, then I can take for delta 2, delta 3, and so on. That means I am proposing that for the parameter space, impose certain probability distribution, and then take expected value of r theta delta 1, r theta delta 2, etc., so that this effect of theta is removed. They become simple numbers. Now you compare them. So the Bayes principle is in the Bayes principle, we assume that the parameter theta itself is a random variable with certain distribution, say tau theta. Okay, so some other name I will use, because generally we use f theta or fx as a distribution of x. So for theta I will use some other thing. So I am calling it, say, tau theta, okay, or pi theta sometimes it is written. So then we can define we can take expected risk function or expected risk as, so let me give some name here, r tau delta, that is expectation of r theta delta. So note here, see, r theta delta is already an expectation of the expected loss, but that is with respect to the distribution of x. Now theta itself is considered as a random variable for which I am taking some distribution name as tau, and over that I am taking the expectation. That means it is something like integral of r theta delta with respect to the this distribution d tau theta kind of thing, whatever. So of course it can be discrete as well as continuous. This is called Bayes risk of estimator delta with respect to the distribution tau. Now there is a name for this. We call it a prior distribution. Okay. So the distribution of the parameter is called a prior distribution. So the class of all prior distributions over the parameter space theta, we will give some notation here. It is denoted by, say, we put some theta star here. Okay. Then estimator delta naught is said to be Bayes estimator with respect to prior tau if r tau delta naught is the minimum of the all Bayes risks. Okay, for all d, for all delta, if the minimum Bayes risk is obtained by the estimator delta naught, then delta naught is said to be the Bayes estimator with respect to the prior distribution tau. So initially the Bayes estimators were looked at with suspicion, because people thought that you can take your prior distribution, I can take my own prior distribution, and therefore we will get different answers. However, it was proved by Abraham Wald and then by many subsequent authors that in any given decision problem, all good estimators are in some sense Bayes estimators, and therefore whether we take this prior or that prior, we are going to end up with a good estimator only. So in that sense, this, so nowadays Bayesian estimation is actually one of the most prominent research areas in statistics. And a lot of prominent statisticians are actually working on that thing. So if you look at from the point of view of calculation, how will you calculate? So R pi, R tau delta. So this itself is an expectation. So you are writing it as expectation of R theta delta. And this itself is an expectation. So this is expectation of expectation L theta delta x. See, the first expectation is with respect to the distribution of x, where theta is considered to be fixed. And the second one is with respect to the distribution of theta. So basically, in some sense, it is double summation or double integral, we can say. So it is L theta delta x fx theta d tau theta. Okay. This first one is over the sample space, the second one is over the parameter space. If we can allow the interchange in the order of integration or summation, so I am writing this as some general forms. In place of fx theta, you can actually write even df here, so that we can take care of discrete continuous both. So suppose we can write down the interchange of the order of integration. So in that case, we can write it as d tau theta given x. So I will put some name here because tau was for theta. I will use another name here. I will put here, say something like pi. Okay. And then this one will become d of gx. So that means the inner one has now become conditional with respect to x, and this one is marginal of x. Here it is conditional of x given theta, and here it is marginal of theta. So we have interchanged the role. This one is called posterior distribution of theta. So one method of solution is that if we minimize the inner expectation for each x, then we get the base estimator. So this is the practical thing. That means how to obtain the base estimator in any given problem. So I will talk about it. What is the time now? Yeah, I think I can just take another 2-3 minutes for introducing this, and then I will move to. Firstly, let me take the definitions here, and then yeah. Now, in mathematics, you know that when we try to find out the minimum value or the least value of a set, then sometimes the least value does not exist, but we may actually come closer to the least value. So there is a concept which is related to the base estimator. It is called epsilon base estimator. That means within the epsilon distance, if we are there, then this is known as epsilon base estimator. So suppose I take epsilon to be positive, then an estimator delta naught is said to be epsilon base with respect to prior pi. So I have taken tau, not pi. Pi is the posterior. If r tau delta naught is within epsilon of the minimum value. Before I tell you how to calculate this base estimator, etc., through some practical problem, I will actually tell you the second principle also, because in the remaining period, let me just discuss that thing. So what is minimax principle? In the Bayesian principle, what we did, that we replaced the risk function by a single value by taking some sort of average value. In minimax also we reduce it to a single value, but the principle is to take the maximum value. Okay, so in this principle, we minimize the maximum risk. So for each estimator delta, the criteria is maximum risk. Actually, in some sense, what does it mean? It means that whatever be the possibility, you assume that the worst may happen, and then you try to find out that estimator for which that worst is the least. So it is something like minimizing the maximum risk. Okay. So in real life situation, we see the examples of such things all the time. That means you try to take the safest path kind of thing. That means whatever action plan you have thought about, and then you think that, oh, if I take this action, then the worst possibility is this one. So according to the worst, you try to reduce the risk. Okay. So we say an estimator delta naught is said to be minimax estimator if the maximum risk of delta naught is the minimum among all estimators. This concept has actually come from the game theory. In the zero-sum two-person game, you have two players having available strategies to them. So each player will make a move according to think that if he makes a certain move, he may suffer the worst. So now which choice will give him the least risk? So this is the minimax principle, which was there in the game theory, and it has been adopted in the estimation. And of course, once again, if the infimum is not achieved, we can remain within the epsilon. So delta naught is said to be epsilon minimax. If the maximum risk of the estimator delta naught is within epsilon of the minimum of the maximum risk. Of course, if we are considering a zero-sum two-person game, then from the other side also the minimax rule can be there. Then the minimax rule from the other side will be actually max min rule for this side. So we have the concept of least favorable prior. Let me introduce this definition of, yes.
This shouldn't be less than equal to.
Yes, thank you. Yeah, it should be less than or equal to, right. So a prior distribution tau naught is said to be least favorable if the minimum base risk with respect to tau naught is the maximum of the minimum base risks among all prior distributions. So this one actually, this one is actually called minimax value. That is the min max, and this is called max min value. And the game is said to have a value, or the problem is said to have an equilibrium point if min max is equal to max min. In tomorrow's class, I will tell you the methods for finding out these base estimators and minimax estimators, and consequently, what are the good estimators in general, that we will tell. So with that, probably we will end up this chapter on the decision theoretic criteria for estimation. And then of course, we will move to some testing of hypothesis. So probably next week I should, if some of the students are there, then I will take in the Nalanda complex. Maybe I will stop today's class at this point of time.